All right, welcome back, everybody. We're moving on to the two final examples in the book of the method of characteristics, just so that you can see me actually work through the method of characteristics rather than just work through what's already been shown on the book. So we'll just get a lot of practice using this method today. Let's make a really quick recollection of what the method of characteristics is before we actually get into this example. So we're here at the actual statements of the theorem. And the idea is that we start with a function of our spatial variables, or even temporal. X is just the independent variables of our PDE, and then phi and its gradient, or the solution we're looking for, phi and its gradient. That would make it first order. If I'm not looking at higher powers of the gradient, then I'm only first order. F here just describes a relationship between each input. Right, so we're just describing a relationship between our independent variables phi and maybe its first derivatives. For example, relationship x partial x phi plus y partial y phi plus phi minus 2xy equals 0. That's a relationship of a bunch of terms of first order derivatives, independent variables x and y, as well as phi itself. So just a giant relationship of those, all of them equal to 0. So we have that sort of relationship. Then we have our single boundary condition. This could be a boundary in time, right? Don't forget that t equals 0 is a boundary, quote unquote boundary. So in some temporal cases, you may have a boundary at time being 0 or time being whatever the initial value of time is. But we have phi fixed on the boundary. It has some function that's been prescribed. This will be prescribed by other knowledge. Let's recall in the case way back to the kind of the first video in the series, we talked about the shape of a soap film or a bubble stretched between a wire, and the wire itself is prescribed for us, right? We determine the shape of the wire, but we don't determine the shape of the soap film. Physics does that for us, or in other words, the PDE does that for us. So the exterior, the boundary, has been determined, and yet the interior gets defined by the PDE itself. And so this is the sort of a problem that the method of characteristics can tackle for us, and the process is a little bit tricky. Within the process, what we do is we relabel the variable x as gamma, so I replace x with a gamma. We relabel phi with a q, and we relabel the derivatives on phi with a vector p. It's boldface there, or if I'm just drawing, I'll put a vector over p. To keep in mind that, the gradient has multiple terms to it, because necessarily our spatial terms need to have multiple directions. Otherwise, we're just working with an ODE and not a PDE. So our gradient will always be a vector. Replace that with the vector p. At that stage, once we've made those replacements, our function f now actually looks like f of the variables gamma, and gamma is a vector as well, right, because x is a vector. Variables gamma, q, and p, and both gamma and p are vectors, equals 0, we use this function f to construct a system of ODEs. We're going to take a gradient in all of the p directions, set that equal to gamma prime as an ODE. We're going to take the gradient in the p directions and take a dot product with p, set that equal to q prime. We're going to take a gradient in the gamma directions, make it negative, and then take a partial derivative in the single q direction, right, because there's only one q there. Take a partial derivative in the q direction and multiply it by the vector p. Okay, so then this will be one giant vector, set that equal to the vector p prime. So that's going to give us a system of ODEs, but if it's a system of ODEs, it either needs itself boundary conditions or initial conditions. And in this case, we can get away with initial conditions by starting on the boundary and trying to evolve into the interior of omega. So the initial condition gamma, the initial condition for gamma will always be an arbitrary point on the boundary. The initial condition for q will always be the value of phi on the boundary point, gamma at time 0. So whatever we decide our initial point on the boundary is for gamma, that we're going to evaluate phi there. But we know what phi looks like on the boundary. It looks like f, so we really evaluate f there for our initial point for q. And then finally, I think everybody tends to have more trouble with these initial conditions for p. Another way of thinking about this, that maybe I wasn't quite as clear about in the last video, is that this bottom row, so the bottom row says, since p, the vector, is defined as the gradient of q, right, because q is just phi, and p is the gradient of phi, so p has to be the gradient of q, we can compute the initial condition for p the vector by computing a gradient of the initial condition for Q. Now the only caveat to this, and this is why there is another line there, the caveat is that the initial condition is only defined within the boundary. And so we miss one direction. There's one direction that we can't actually compute a gradient in because this is only defined on the boundary. Since that's only defined on the boundary, you can only take a gradient in the directions of the boundary. And we're missing exactly one other direction. That's the direction normal to the boundary. Okay, so we miss one direction, which is normal to boundary. It's just impossible for us to calculate that direction. And this is where satisfaction of the PDE gives us that final calculation we need. So the final calculation, the final normal direction for P at time 0 comes from the rest of the information we have and the PDE itself. So it's this combination of all of those that are going to give us the initial conditions in P. Once we have our system of ODEs, we can solve it, and solving it's not usually too terrible. It's usually not the hard part here. The hard part is finding the initial conditions, especially in terms of P correctly. And then the next hard part is this idea of inverting gamma at the end. The next hard part, once we solve the ODEs, is inverting gamma. Since, okay, we have Q as a function of time, and we have gamma as a function of time, which equals x eventually. We want phi, our solution, to be a function of x. Well, that is phi of gamma of t. That should be okay. But somehow we need to translate. The tricky part is starting with Q and translating it to phi of x. The way you pull that off is by writing phi as Q of gamma inverse of x. And the Q should not have a vector over it. So Q of gamma inverse of x is phi. So you somehow have to find that gamma inverse. Gamma inverse is the tricky part. So let's jump back into our examples. So here's our second example, and we've got the PDE given here. It's defined on the unit square for omega, which means we're looking on the boundary of the unit square. It looks like on the boundary we're just equal to x1 and x2. And we're looking for a function for which if I take a derivative in the x1 direction, multiply by a derivative in the x2 direction, I recover x1, x2. So put this in the form, let's put it in the form of f of a vector x, phi, and its gradient equals 0. That means I need to move everything non-zero to the left-hand side. It's not too bad. I'm just going to grab x1, x2 and pull it to the left. Now I've got partial x1 phi, partial x2 phi, minus x1, x2 is 0. I'm looking at the left-hand side here. This is f. And then I'm going to relabel f. I'm going to relabel my variables. This is going to be p1, because that was partial x1, right? So in the first direction, the derivative in the first direction, the derivative in the second direction is p2. x1 I'll call gamma 1, and x2 I'll call gamma 2. So what I end up with is my function f of gamma 1, gamma 2, q, p1, p2 is directly above here. It's going to be p1, p2 minus gamma 1, gamma 2. If I scroll down a little bit, see that's what I have right here. Then I'm going to compute my derivatives of f in the correct way. So let's take a gradient in the p directions. That's going to be a partial derivative of p1, which will leave me with a p2. Partial derivative of p2 leaves me with a p1. I can also take a derivative in the q directions. Notably, there's no q there, so the derivative is going to be 0. And finally, I can take a derivative in the gamma directions, where I take a derivative in the gamma 1 direction, I'll get negative gamma 2. In the gamma 2 direction, I get negative gamma 1. So those are the only derivatives of f I need, and this allows me to immediately set up my system of ODEs. So this lets me set up the left-hand side. Let's not forget what the left-hand side is supposed to be. How did I actually set this up? This is exactly the gradient in the p directions. This is always the negative gradient in the q directions times the p vector, but that's 0 times the p vector, so it's gone. And then negative gradient in the gamma direction, so I've got a negative in front of that. That's going to make both gammas positive. So that's why I've got gamma 2, gamma 1 there. Finally, what does q look like? Q is always going to be p dot nabla p of f. So I'm just going to take the vector p and dot it with gamma, whatever I had for gamma prime, equivalently nabla p of f. So if I take the vector p and I multiply it by nabla p of f, I'm going to end up with a p1, p2, and a p1, p2. And I'm going to add those together to get 2 p1, p2. So there's my system of ODEs. Let's get a little bit more clever about what's going on with the initial conditions. As always, gamma just starts arbitrary. And I'll put this in quotes. It's in the boundary. But, for the most part, we just let that be somewhat arbitrary. Because in this boundary, both x1 and x2 could be non-zero. We're looking at the boundary of the unit square. And then q is just the evaluation. This is phi on gamma. And let's just scroll back up to our initial condition here, our boundary condition, phi on gamma. If I put an arbitrary point in the boundary, I was calling that x10, x20. And that's going to be q on the boundary. And then finally, p on the boundary is always the tricky one, right? And nobody likes p on the boundary. So what is going on here? This term right here is f of p0, gamma 0, and q. I know I put my variables in a different order there, but whatever. Plug p of the initial condition in to f. There it is. Plug gamma at the initial condition in. There it is. Plug q at the initial condition in. Q's non-existent in this one. So we have that equation. That's one equation. And then what is this other system that I have here? This is actually the derivative of q0, this function right here, x1, x2. It's the derivative of that in the direction of the boundary. Okay, so what does my boundary look like? There it is. This is the unit square, 0, 1, 0, 1. Sometimes I can exist here, in which case the direction is to the right. This is the x1 direction. Partial x1. Sometimes I can exist here, that's the partial x2 direction. Okay, so there's two cases. The two edges, I'm in the partial x2 direction. The other two edges, I'm in the partial x1 direction. So let's figure out when I'm in the partial x1 direction. Well, that's when x2, my height, is equal to 0, or my height is equal to 1. Right, when my height's 0 or 1, I'm going to take a derivative in the x1 direction. Derivative in the x1 direction here gives me x2, 0. When my length or my width are equal to 0 or 1, I take a derivative in, right, there's my length or my width is equal to 0 or 1. I take a derivative in the x2 direction. Taking a derivative in the x2 direction gives me x1. So that's where those other terms are coming from. So I've got a collection of a few different terms to help me decide the initial values of p, depending on where the initial condition starts. Okay, so I have to keep in mind that the entire boundary is available to me. And when I'm solving this, I need to just choose some point on the boundary. Depending on which point I choose, some different collection of those are going to be my initial condition in P. So we'll see how that plays out in a little bit. There I described where those initial conditions for P come from. So let's actually look explicitly at my PDEs, or my ODEs. I've got this system here. Gamma prime is P2, P1, and P prime is gamma 2, gamma 1. If I restrict gamma 1, P2, and then P2 prime is gamma 1, and I combine these together, you can imagine if I took another derivative here, let's take another derivative here. That relationship comes from the first equation, but now I see P2 prime here, which the second equation tells me is gamma 1. So really I have this second order ODE in one dimension for gamma 1. I could play the same game with gamma 2. I would find the same second order. Gamma 2 double prime is P1 prime, which is gamma 2. So I have this second order ODE in the gamma directions, but they only depend on themselves, and then I can play the same game with the P's to find that those are also second orders that only depend on themselves. The solution to second order ODEs that only depend on themselves are going to be e to the t or e to the negative t. It turns out in this case we need only e to the positive t. So when we solve our ODEs in this case, we're going to get e to the positive t times the initial condition. When I put those in for both gamma 1 and P2, I can plug those into Q. let's recall what q, or q prime, right? I've just found both p's and gammas. They're basically the same thing. But the initial condition for q is going to be 2p1, p2. And when I just found out what p1 and p2 are, there's p2, there's p1. I just directly plug them in to q prime, and I find this expression, which has no dependence on q. So all I have to do to solve this is integrate, and find constant. Once I integrate and find the constant, we recover that as the integral for, or the solution for q. Okay, so I've got q. What I want, I have q in terms of x1, 0, x2, 0, and t. But what I want is I want phi in terms of x1 and x2. So what I need to do with gamma is invert to find gamma inverse of x1, x2 as some expression that depends on maybe x1, 0, x2, 0, and t. It turns out, recall my boundary, it turns out that if I decided to initialize at either x1 being 0 or x2 being 0, that's this point here, this boundary here, or this boundary here, it turns out that I'm not characteristic. This is, violation of the non-characteristic condition. And that's not an invertible system. But if I decide to start on my boundary on these other two places where either one is equal to 1, then I do satisfy the non-characteristic condition, and I push into the interior like I would want to, and I can invert this expression in terms of x1 and x2. So let's do that. Let's do it when x1 is equal to 1. That's me replacing this. x1 equals 1 is this vertical portion of the boundary. We're just going to replace x1 with 1, and we recover this system. We're going to solve for t and x2, 0. If we go through the process of solving for t and x2, 0, it's just a system of two equations with two unknowns. We're going to get that t is log of x1, and x2, 0 is the ratio of x2 to x1. What do I do then? I grab q, right, there's q. I let t be log x1, and I let x2, 0 be x2 divided by x1. And then recall that we were saying x1, 0 is 1. Okay, so if I replace x1, 0 with 1, x2, 0 with x2 divided by x1, and t with log x1, what I end up with is e to the 2 log x1, that's x1 squared. x1 squared divided by x1 is just x1 times x2. What I end up with is x1, x2 is phi of x1 and x2. So you find your solution at least emanating from the right-hand side of the boundary. You could find the solution emanating from the vertical side of the boundary too, and you would recover the same expression. We get that phi is x1, x2. Moving on to the final example. This one's maybe a little bit trickier. It's called Berger's equation. This equation actually describes wave motion differently than the wave equation. This one is a nonlinear wave equation. So in chapter 4, we'll encounter the linear wave equation. This is a nonlinear wave equation which allows for braking. So we're thinking like in terms of if you go out surfing, you don't want to get caught when the wave breaks. It's going to throw you into the water unless you're a really good surfer. But in general, you don't want to get caught when the wave breaks. Wave breaking in the sense of, the water falls once it reaches a peak where it actually has the ability to fall instead of just a wave moving to the right. So that's the Berger's equation, and it looks like the following. It's really not too complicated of an equation. We're going to give ourselves an initial condition, which looks a little bit funky. This is really just a piecewise function. Give ourselves the initial condition 1, that's where x equals 0. Then we fall linearly until x equals 1, and then we're 0 over here. So that's not too crazy of an initial condition. And we're going to allow time to move forward, so this is going to move to the right. And we're going to see some sort of wave behavior happen here where waves could break. The idea is that if this is a wave, then kind of this raised portion of the water should move to the right. And the idea is that it breaks when it gets to a vertical peak like this. If we extended it farther, then it would actually get to something like that, and then it would start breaking. So that's what we're going to see here if we solve this correctly using the method of characteristics. Let's make sure we can find our function f. So if we decide to send ourselves to f of x, q, and p, recall x as a vector here can include times sometimes, right? So really this should be thought of as f of t comma x, the one-dimensional x, q, and then partial t of phi and partial x of phi, which is just p1 and p2. Okay, so what do we have? That's going to be p1, that's going to be q, and that's going to be p2 is 0. So there's my function f. Well, that's the function f. So not too hard to find f. It'll be a little bit harder to find our initial conditions. So as before, there's my function f. And if I relabel the initial conditions at q0, we get the following. Sorry about the bad typesetting there. Okay, so having found f right here, we can compute the derivative in p, right? So I'm just going to take a gradient in the p1 direction. That's going to be 1. In the p2 direction, it's going to be q. We take a derivative in q, that's just going to give me a p2. And finally, the derivative in the gamma directions will be 0 because gamma hasn't shown up at all. With that said, gamma prime is always going to be the gradient in the p directions. There it is. P prime is a little bit tricky, right? This is always going to be negative gamma directions in gamma, which is 0 in this case, but we also have this minus the derivative in q, which was p2 times the vector p. So really here we have a negative p2 times the vector p1 p2, so we get negative p1 p2 p2 squared. That's what we see at the bottom there. The initial conditions, ideally everybody can figure out where those come from. The first term in gamma is equal to 0 because we initialize at time t equals 0, right? The wave equation, or the Burger's equation, is beginning at time t equals 0 there. So every point on the boundary is a t equals 0 point on the boundary. And then we can start anywhere in space, and q is always going to look like you would expect it to for anywhere in space. That's the way it was defined from the beginning. But let's talk about p. So what I've done here is just exactly copy the PDE for this first term here. That's exactly the PDE, right? It's P1 plus Q, P2 is 0. That's the exact same PDE we were originally working with. The second term, let's note where this comes from. It's piecewise, right? And we're always taking a derivative of Q in the direction of the boundary. Let's note that the direction of boundary is specifically the spatial direction. And the spatial direction here is partial x, or in terms of the boundary is partial x0. So I'm just looking at q here, and I'm taking a derivative in the x0 direction. So the derivative of 1 is 0, the derivative of 1 minus x0 is negative 1, derivative of 0 is 0. So that's where those three terms come from, and those are my initial conditions. I then can get away with solving this system. Let's think about what would be the easiest way to solve this system. I don't know q right now, q prime, because I don't know p yet, so I don't actually know gamma prime because I don't know q. But let's notice that all of the p's only depend on p's. So we can try to solve the p directions first. So we're going to do that. And then what's extra important about the p's, even though this is a nonlinear system, which tend to be really tricky to solve, it's actually a nonlinear one-dimensional ODE, and specifically the p2 variable. The p2 variable is isolated. So it's all by itself. I can solve that equation by itself first, jump myself up to this equation, because once I know what p2 is equal to, I can jump myself up there. Once I know what p1 and p2 are equal to, I can jump up here. And once I know what q is equal to, I can jump up here and find gamma. So I can find all of those if I just work in a very clever way. That's what I mentioned here, a natural ordering in which to solve these ODEs is as follows. And so we go ahead and solve this. So this is going to be a separable ODE. Once I get to this place, this is going to be a first order linear ODE in one dimension. At this stage, it's also first order linear. And then at this stage, it's just an integration. And at that stage, it's just an integration. So I'm going to go through and solve all of those along with the initial conditions, right? P2 has a very particular initial condition there that I'll have to make sure I meet piecewise. And when I do that, just going to solve this using separable methods. We find out that P2 is 0 on both sides of the non-exciting portion. It's equal to 1 over s minus 1 in the exciting portion of my boundary. Then since I know what P2 is, I plug that into P1 prime, and we can solve P1 prime as, it was first order linear, you'll recall, as 1 minus x0 over 1 minus s. Once I have P1, I plug those into Q, both P2 and P1, I plug it into Q, and I solve for Q using first order linear methods. And And we find out that Q is really not tricky at all. It ends up, a lot of things simplify. You end up with 1 minus, Q is just constantly equal to what you expect it to be on the boundary. And then finally, once you know what Q is equal to, you can solve for gamma. And solving for gamma 2 consists of just integration. So I'm integrating 1 to get S plus an initial condition. I'm integrating 1 minus x0 to get S times that plus an initial condition. And I'm integrating 0 to get an initial condition. So that's going to be gamma 2. Finally, gamma 1, since gamma 1 prime is equal to 1, gamma 1 is just going to be equal to S plus an initial condition, but S and time are the same thing. So I start at t equals 0. We end up with gamma 1, gamma 2 being gamma 1 is S, and gamma 2 is that piecewise function. We're going to try to invert. This is finally step 3. Try to invert system in gamma. So gamma 1 equals t, gamma 2 equals s. We're going to solve this for x0 and s. And it's not actually that, it's not hard to solve this for x0 and s when we set it up, but it's not exactly easy. I mean, s and t are the same thing. That's clear from the beginning. But to invert this system in terms of x and t is not the easiest. So you just kind of take your time and make sure that you keep track of each portion for which x naught and s occupy certain areas, and you invert it in each one of those portions, and you get these three functions in those areas. So now you're going to notice that this inversion, this is multi-valued at time t equals 1. That's because if I put a 1 here, I have x is less than or equal to 1, and I also have x is greater than or equal to 1. But here I get x minus 1, and here I get x, which are two different expressions. So this loses well-definedness at x equals 1. And we actually have kind of a nice example of something called finite time blow-up. And this is what I was saying from the beginning. That's our initial condition of the wave. And as time moves forward, this part of the wave is going to move forward and eventually get vertical, and eventually it's going to want to break. And it's that breaking point where you would end up with an ill-defined function, because if this is a scalar field, it's going to have multi-values here, because there's going to be a value of the wave up top here and a value of the wave at the bottom there. So this is an example of finite time blow-up in PDEs, which is certainly common for nonlinear PDEs, especially fluid dynamics PDEs. Okay, that's all I've got for today, but we should talk about this a lot in class, because I know these get pretty tricky, and we should spend a lot of time working on these. So I'll see you then. Bye.